Welcome to the Theoretical Neuroscience Podcast. I am the host, Gaute Einvoll. Until a few decades ago, neuroscientists could only measure action potentials from a few or maybe a handful of neurons at a time. Hubel and Wiesel's discovery of orientation and direction selective cells in the visual cortex was made by recordings of spikes, the extracellular signature of action potentials, from a single neuron by a single electrode lowered into cortex. From such recordings, they could compute so-called tuning curves, showing how the firing of spikes depended on, for example, the angle of orientation of an elongated visual stimulus. Now we have so-called multi-electrodes, that is, electrodes with multiple electrode contacts that together can measure spikes from hundreds of neurons simultaneously. But what do you do with a collection of recorded spike trends from, say, 100 neurons in the cortex? How do you analyze the data to learn about the system you are recording from? One can, in the spirit of Hubel and Wiesel, compute 100 individual tuning curves, but this is not always the best option. In fact, for recordings from the motor cortex of monkeys, it has turned out that one can learn much more from the data by focusing more directly on population dynamics by doing so-called dimensionality reduction. For the case of 100 neurons, we can represent the neural activity in a 100-dimensional space with each of the 100 axes giving the firing rate of one of the 100 neurons. However, in experiments where a monkey has to reach out in certain directions according to instructions, it turns out that the trajectories that these 100 neurons follow in these 100 dimensions lies in a small subspace. This subspace has a much lower number of dimensions than 100, maybe even as low as 3. Further, the population dynamics on this low-dimensional manifold can effectively be described by the dynamics of so-called latent variables. These latent variables summarize characteristic population-level spike patterns when moving on trajectories in the low-dimensional manifolds. They turn out to be very useful when you want to compare different recordings. The reason is that they provide a common low-dimensional coordinate systems that can be aligned across recording sessions and even between monkeys and possibly also between monkeys and humans. In a musical orchestra, it is the overall combined sounds from all instruments that deliver the musical message, not the sounds from an individual instrument. So if an individual violinist stops playing, you can typically still recognize the orchestral piece. In a similar way, in the motor cortex, the neural message is conveyed not by an individual neuron, but by a collection of neurons. And if an individual neuron stops working, the main information is not lost in general. Today's guest, Sara Solla, is one of the pioneers in development and use of manifolds to analyze neural data, in particular from the motor system of monkeys. In the podcast, we talk about the history of motor cortex research and why the single neuron analysis that was so successful in the visual cortex was less successful in the motor cortex. We next talk about neural manifolds and manifold analysis and how this mathematical tool came to be critically important for analysis of multi-electrode recordings in the monkey motor cortex. We further talk about results from various studies using this approach and also how manifold analysis may help developing accurate and robust brain-computer interfaces. Like many theoretical neuroscientists, Sara Solla has a background in theoretical physics. At the start of the podcast, before we move on to manifolds, she tells about how a talk by John Hopfield inspired her to work on neural networks. One outcome of this was a joint paper with Jan LeCun of AI fame, suggesting improvements of learning rules in artificial neural networks. This paper was published in 1999 and has now been cited 7,000 times, with an explosion in citations the last 6-7 years. Note that I had some technical issues during the recording, so my sound is less good than what is usually the case. Fortunately, Sara's sound is better. If you want to support the podcast, go to patreon.com/theoretical neuroscience podcast and choose a membership of your liking, for example, at the cost of $1 per month. As a member, you will get access to a video version of the podcast recordings as well as transcripts of each episode. And note that there is a 7-day free trial period when you sign up. I also have a YouTube channel called Theoretical Neuroscience Podcast, where you also can watch the videos. I really appreciate all of you who are already Patreon supporters. Thanks a lot. I will be most grateful if more join in to help me fund the production of the podcast, even if you're not too interested in looking at the videos. But I also appreciate all the other listeners, and I hope that all of you can help spread the word about the podcast to other people in the community, on social media or otherwise. Okay, here is Sara. So, welcome to the Theoretical Neuroscience Podcast, Sara Solla.
Thank you, Gaute. Thank you a lot. Thanks a lot for the invitation. I'm delighted to be here.
Yeah, excellent. So, we thought, now you live in the U.S. I think you're a professor at the Northwestern University for like 30 years almost, and working in the medical department. But before that, I think you came from Argentina doing physics, or
I I came to the United States. Next year is going to be 50 years ago, so it's really a lifetime here. But when I came, I had my degree from the University of Buenos Aires. My degree is called licenciatura, which is equivalent to a master's. It's a 5-year degree, and it includes a short master thesis. And I majored in physics with a minor in mathematics at the University of Buenos Aires. So that was my background when I came to the United States. I went to the University of Washington in Seattle as a graduate student. I did my PhD there with Eberhard Riedel, and my PhD was really statistical physics, renormalization group. I studied XY models that at the time were very fashionable because of the Costa-Lithales transition and the role of vortices, the role of singularities.
I see.
And I studied XY models in 2 dimensions in the presence of bond dilution. So it was a combination of XY models with percolation. And it was a very good education because the XY models are very beautiful because they have maps into a lot of other models. They map into solid on solid models. I love
Because
temperature.
most of the XY model is some kind of
It's
spin
a
model,
planar
isn't it?
spin. It's a spin that rotates in the plane.
Yeah.
And you can map it into a solid on solid model at low temperatures, and you can map it into a Coulomb gas, the gas of vortices at high temperatures. And so it has all these very nice anchors where you can do exact calculations. And then when you introduce percolation, then there are connections with random resistor networks. And so it was a very, very
I
nice
guess
education, general education on.
because I guess many of these listeners are probably a bit confused about all you said, but what it illustrates is that you are one of the, I guess, many pioneers in neuroscience, computational neuroscience, that came from statistical physics, right?
Exactly. So my background was very much statistical physics. And then I went to do my postdoc at Cornell University. And I was a postdoc with Neil Ashcroft, who was a very traditional solid state physicist.
I know. I have his
So
book with Ashcroft and Mermin.
the Ashcroft and Fermi is the Ashcroft of the Ashcroft and Fermi book on
Yeah.
condensed matter physics. So I was working with Neil. I was using all my percolation and random resistor networks background. And you will laugh when I tell you what was my project. We were working with experimentalists that had thick films of granular vanadium dioxide, and these thick films had metal insulator transitions.
Okay.
So I was studying them from a percolation point of view, doing the crossover from 3 dimensions to 2 dimensions because there were films that were thick films. So some of the properties were 3 dimensional properties. And I was doing my postdoc there and, talking to other students and to other postdocs. It was a very wonderful environment, really. At that time, Cornell, the solid state physics had um, an umbrella grant that supported, I think, 4 or 5 postdocs. So the postdocs were not postdocs of any specific professor. We were postdocs of the Laboratory of Atomic and Solid State Physics. And so we had a lot of freedom, really, to interact with each other and to interact
Mm,
with students, to interact with other professors. Um, but I was in that wonderful environment, and I went to a meeting of the American Physical Society.
mm. The
And
March meeting.
this is the March meeting, and
Yeah,
this is a
exactly.
meeting a little bit like the SFN meeting.
Yeah.
Many people, many parallel sessions. So before you go, you take your planner and you decide which are the sessions that you want to attend, and most of them are short, 10-minute talks, and
Mm,
you're running from one session to the next. And suddenly I had a gap in my schedule. There was a whole hour and a half where I didn't have anything scheduled. So I thought I shouldn't go to a short talk because a short talks, if it's not your field, it's very hard to understand,
understand.
very hard to
Mm,
follow. So let me find a plenary talk, a 1 hour talk that I will learn something, at least the beginning. So I look at my program, and there is a guy from Caltech called John Hopfield giving a
yeah,
talk.
exactly.
So this is 1983, mind you. So his
Mm,
82 paper was out, the 84
uh,
paper was not out. And I go to this talk, and I know all the mathematics because although I didn't work on spin glasses, I took courses on
mm,
critical phenomena. And one of my courses included a whole 2 or 3 weeks where we learn spin. So I knew all about these landscapes, where you have many minima. But
mm,
this guy was talking, so I knew the mathematics, but he was talking about storing memories
mm.
at the minima and then recovering memories by putting the system somewhere and letting roll downhill to
Yeah,
get to the minimum. And Gaude, it was the most exciting thing that I had ever heard
yeah.
in as an a graduate in Argentina, as a graduate
Uh,
student at the University of Washington, in my year of postdoc at Cornell, I had never heard anything so exciting.
mm,
And I thought, this is what I want to do.
mm,
This is really what I want to do. So when I was looking where to go next, I decided to go to IBM because Scott Kilpatrick had come up with this simulated annealing
mm,
algorithm it was a way to solve optimization problems in a manner that was also, you go downhill in this complicated landscape, and sometimes you go uphill a little bit to go over a barrier. So it was a little bit of a Monte Carlo idea combined with gradually lowering the temperature so that you'll be confined with the.
mm,
So I thought this is sufficiently close to what I want to do. I will go there.
mm,
But I was a bit frustrated because there wasn't much going on in terms of neural networks. But there was a young colleague in the mathematics department, and that was also interested in these ideas. And we did some work together. Actually, what we did is they use simulated annealing to solve the placement of electronic parts within an integrated circuit. And when you do simulated annealing, you get many solutions. If you keep on, you restart it and you run it again, you go to a different minimum every time. So we had a collection of solutions. And according to Parisi, all these equivalent ground states should have an ultrametric structure if you follow the spin glass literature. So
okay.
these minima should have we should be able to put them in a tree, and where the distance is defined by going up the tree and down the tree again,
Mm,
and all the triangles are isosceles, and all these. So we look at this. We took as data this collection of solutions, and we verified that they were ultrametric, that they were
mm.
organized according to the Parisi
Ah,
scheme for spin glasses. So there was a meeting in Les Souches with many interesting people. Jan LeCun was there
mm,
talking about really talking about back propagation, except that neither we nor he and nor him understood the importance of this. This was I have to think 83 or 80, 84 maybe. Stuart Kaufman was there of the cellular automata, of course. Derrida was there. Changeux, who is a very prestigious French
Mm.
neuroscientist, was there. It was, I think, the first meeting where people got together from physics, from neuroscience, from computer
Mm.
science to try to see what was going on. And I gave a talk about this paper that that we had done with Greg Sorkin, who was the name of my IBM colleague. And I went back, and I was still frustrated at IBM and thinking, what should I do next? And then I get a call from a guy who says, well, my name is Larry Jackal, and you don't remember me, but I was at this Lesouche meeting and I heard your talk, and I've been charged on creating a new group at Bell Labs, which is
Ah,
going to be a neural networks group, and I wondered if you would like to join us.
oh,
So
that's a
I
nice
went
clue.
for my interview, and I had a good time, and I joined them, and I worked there for 11 years. It was really fantastic because I joined in 86, which is when the backpropagation algorithm came out.
Mm.
And so we were immediately moved from the Hopfield networks, who were recurrent networks, to the multi-layer networks.
Mm.
And a year later, Jan LeCun joined us, and we started working with the idea of convolutional networks, and started making networks for image processing and pattern recognition. We
Mm.
started working on the famous digits database, where you're trying to do recognition of the
Yeah.
10 digits. And
MNIST, right?
yeah, and the MNIST
Yeah,
database,
exactly. Mm.
exactly. And
Mm.
so it was a fantastic time.
Mm.
Vapnik visited us for a couple of years. Isabel Guyon was there.
Yeah.
Corina Cortez was there. Jane Bromley.
Because
Um,
I checked your like just like your publication and citations, and you have one paper with Jan LeCun and some J. Denker, which has almost 7,000 citations, and all of them almost came after 2018, even though it was published in 89.
it's a fantastic paper.
Yeah.
The third author is John Denker, who was
Mm.
also part of this group. And so the idea, people were beginning to try to prune the neural networks. So you
Mm.
train them, but they are very hard to interpret. And we thought if we could remove weights and make a more sparse connectivity network, maybe it will be easier to understand what is the computation that the network is implementing. And these people were thinking of deleting the weights according to their absolute value squared. Just, the weights that are small, let's delete them. But then we were having lunch, the three of us together, and I think it was Jan's idea. He said, look, think of the error as a function of a weight. Of course, the weight space is very high dimensional, but
Mm.
let's think of one of those dimensions, one weight. And so here is the learning error, and it has a minimum, and
Mm.
that's how we find the correct value for that weight at the minimum. So we are at the minimum. The first derivative is zero, it's a minimum. So the lowest expansion is to do a parabola, to use the second derivative to construct a parabola. And now, if we cut that weight, we can use the parabola to see by how much does the learning error increase if we cut
Mm.
that weight. So if you compute that increase in the learning error is one half times the second derivative
Mm.
at the
Let me
minimum
know.
times
Mm.
the value of the weight squared. So it's not the value of the weight squared that
Mm.
matters, it's the value of the weight multiplied by the second derivative.
Okay.
So we call this the saliency. And we said once you are at the minimum, you should compute the saliency for all the weights and remove the weights with low saliency.
Mm.
Because if you are in a very shallow minimum, you can cut it and the cost will be very small. But if you're in a very deep,
Mm.
very sharp minimum,
Yeah.
if you cut that weight, the penalty will be very high. So it's
Mm.
clearly the second derivative that matters in
Mm.
combination with the weight squared, not just
Mm.
the value of the weight squared. So Jan did some simulations to show that this was a good way of pruning the network. I wrote the paper. John Denker came out with the optimal brain damage title.
Yeah.
And we had a paper in 2 weeks. It was
Yeah.
unheard of. I mean, and we submitted it to Neurips, which at the time was called NIPS.
Mm.
And it was used. It has citations, it was used, but then with deep learning,
Mm.
with the explosion of deep learning, there is an explosion of citations. It's a very useful, it's a very simple algorithm.
Mm.
You don't have to keep track of the second derivative all the time. You only compute the second derivative once you have reached the minimum. And you compute it by backpropagating the same way you compute the first derivative
I
all the
see.
time. So
So
you
it's
lower by
used in this.
saliency, you cut 10% of the weights, you
Mm.
retrain, and you cut 10% again. At some point, the network is not good anymore. So
Mm.
you stay with the smallest network that is
I see.
functional, and then it's easier to interpret it.
Huh. So this is actually used in also these deep networks, which are the most applied. I mean, the ones that you use all the time, or
It's used all the time. This is why
yeah,
we, as you pointed out, the citations
yeah,
are
no,
enormous
yeah,
recently. And whenever Jan and I meet, we laugh because this is our most cited paper,
oh,
really.
yeah, yeah. It's sort of, but it's something really cool about the physics that you can have this cool idea and publish in 1989, and
Yeah,
it comes back 30 years later and turns out to be
yeah.
really important. That's sort of cool.
It makes you feel that you did something really useful, right?
Yeah, well,
When it
absolutely.
arrives again, and so many people find
Yeah,
that it solves the problem for them.
yeah.
And it was just a really
Mm.
simple idea in retrospect, but it worked. So.
Mm. So, and then I saw you also had the one paper with John Hopfield, I think.
Yes, so at that time, so we were in Bell Labs Homedale, not
Uh,
Bell Labs Mary Hill. And one of the things that my group was trying to do was actually creating chips that would, in an analog fashion, implement the Hopfield networks.
okay.
And Hopfield at that time was still at Caltech, not at Princeton, but he visited, because
Mm,
some people in Murray Hill in the theory group were doing Hopfield networks from a statistical physics point of view, analyzing
mm,
them. So he
mm,
visited them and then he visited us. And we had moved away from the recurrent networks. As I said, we're working more on the layer networks, the multi-layer perceptrons. And we were developing these ideas about how can it be that you trained with a very relatively small number of examples or large number of examples, but you give these examples, so you memorize the examples in some sense. How can the network generalize?
mm,
How come that when I give it an input that was not part of the training set, the
mm.
network gives me an output which shows that the network has learned the rule in some sense,
Yeah.
beyond memorizing these input output pairs that were the training set. And we began to have developed these ideas of entropy reduction. So we were discussing the emergence of generalization. We didn't have a complete theory, but we had. And we discussed these ideas with John, and John thought it would be a good idea to write down what we had, even if it was not a complete theory, because it would stimulate other people to think along those lines.
Mm,
So we wrote this paper with John Hoffman is a co-author, and it's
yeah.
I
So
have to tell
cool.
you something funny about that paper. So we, of course, we were all using LaTeX at that time as
Mm,
snippet. And in LaTeX, when you want to control the size of the font, you can put a backslash large,
mm,
and you can use large with lowercase or large with capital, and then it becomes even larger.
yeah. Mm,
So we put slash large um, learning and rule extraction and this, but large was supposed to be an indication for the size of the font. Well,
Ah.
somehow the backslash got lost by the time, and we didn't notice it. So the paper now, you always laugh when we see it. It says large learning or something like that. And the large was just supposed to mean a formatting
I
instruction
see.
for
Oh
latex.
well.
That font.
Oh well. It
But
could
it,
have been could have been worse. Could be tiny, and there's all kinds of other font
you know,
sizes.
that's
Right?
very funny. And it's very funny now because, they are called large language models.
Yeah.
And the deep learning is, you need large training sets. So it
Yeah.
ended up being a very useful word to have in the title of the paper. But
Yeah.
it
I
was
see.
a complete
Mhm.
accident and
Mm.
misunderstanding. Yeah.
So, and you were also at some time, were you? Because I'm Norwegian, so we went to this Nordic Institute of Theoretical Physics. So you
Right.
were also there a little bit, or how was it? I just remember you from
Well,
there. I
this
think.
is this is when I was at Bell Labs. So
Yeah.
when I met my husband Predrag Svitanovic, I was working at Bell Labs and living in New
Mm.
York, and he was a Carlson professor at the Niels Bohr Institute.
Ah, exactly.
He really, really enjoyed being in Denmark. It
Yeah.
was, he. So
Well.
I said, well, I should make an effort to find a job in Denmark.
Mm.
So I asked for a leave of absence. Bell Labs was very generous. They gave me 1 year leave of absence, not with salary, but then maintain my
Mm.
benefits, my health insurance, and
Yeah.
my pension plan. It was incredibly generous. So I spent a year in Copenhagen. I think I
Okay.
was 6 months supported by Nordita and 6 months supported by the Niels Bohr. But at the
Okay.
time, it was the same building, it was. So
Mm.
I spent a year there and I applied to every position that came up.
Mm.
But, it's a small country. There are not that many positions.
Mm.
And I was a little bit frustrated, if I can say,
Mm.
because there was such a strong preference for local people.
Yeah.
And it got to the point at the end where I knew, I had a permanent job at Bell
Mm.
Labs. I
Yeah.
was not a postdoc or an
Yeah.
assistant professor.
Yeah.
Um, and
Mm.
I felt that they felt that Predrag was never going to leave. And as long as they paid me,
Mm.
sometimes from here, sometimes from there, and they gave me a desk, I was going to
Yeah.
stay. And I was
Yeah.
not going to do that.
Yeah.
And at some point, I felt that I was competing against people that if I was competing against them in the States for a job,
Mm.
I would
Mm.
come on top.
Yeah.
So it got really frustrating. So I went back. I went back at the end
Yeah.
of '95,
Mm.
and then during '96, Predrag and I began looking for
Yeah.
positions in the States. And in '97, we both moved to Chicago, to Northwestern.
I hope that it has. It certainly was a problem. Sort of like at many Nordic universities, also Norwegian universities, that we tend to hire people and sort of never been out of the university even. So instead of sort of getting fresh minds from the outside, and I hopefully that has changed at least to
Right.
some extent. Yeah. Anyway.
What, what I was surprised, Gaute, this was so much against the spirit of Niels Bohr.
Yeah.
Because if you think on his board and his institute,
That's true.
he
Yeah.
just gathered the best people around and it
That's
didn't
true.
matter where they were from.
That's true. Yeah.
And so that was a little bit of an abandoning this
This idea.
spirit
Yeah.
of excellence for the spirit of more.
Mm.
But it's understandable that you want to protect your own people. So anyway,
Well, I mean, your own people can also go abroad, right, and get the job in you. I mean, it's if you think of it as an international market, then
yeah,
yeah.
the
Anyway,
ones that are good enough can. Yeah.
yeah. So
So
anyway, so but
anyway, that's how
you
I ended up at Northwestern. Also, because in the meantime, in my last years at Bell Labs, my group had become a little bit more engineering oriented
mm,
because we had networks that really did fantastic jobs at
mm,
recognizing characters and automatic reading
yeah,
and image processing, auditory processing. So once you have a successful thing, it needs to be more like a product. It
mm,
needs to be user friendly, and you
yeah,
end up doing a lot of things that are not at the scientific end. but at the engineering end.
Yeah.
And I myself have become more interested in neuroscience. Okay,
Mm.
this is how our neural networks do it, but how do we do it?
Mm.
How
Yeah.
and I began to this meeting NIPS at that time had a strong neuroscience component. We went every year, and I began to talk more to my neuroscience colleagues, asking them what to read, what to. And the interesting thing for me at Northwestern is that they were willing to hire me in the neuroscience
Mm.
department. That was at that
Yeah.
time called the physiology department, and is now called
Mm.
the neuroscience department.
Mm.
And this was a fantastic opportunity for me because it was very hard the first couple of years because I didn't have the background. I
Mm.
had a lot to learn, but I had very
Mm.
generous colleagues that
Yeah.
were willing to spend time with
Yeah.
me and teach me and to collaborate with me. And, I had enough colleagues who saw the value of modeling in a more quantitative manner and modeling not in standard statistics, because in standard statistics you use a package
Mm.
and the
Yeah.
package
Yeah.
doesn't know whether your data is neurons or your
Mm.
data is a stock market or your
Mm.
data is the propagation of a disease. It's just that statistics, in a
Mm.
blind
Yeah.
manner. And although there are many things about the brain that we don't know, there are many things that we do know. And my point of view has always been, since I made this transition, that we should create models that incorporate what we know about
Mm.
the question that we are
Yeah.
asking,
Yeah.
about that area of the brain, the connectivity, the dynamics. We should put these things into the models. So we
Mm.
have to go beyond the classical statistics and do what I call model based data analysis.
Mm. Mm.
So I've been very lucky that my colleagues, some of my colleagues were interested, and then also, I've been at Northwestern since '97, so it's going to in a couple, it's 28 years now,
Mm.
and in the meantime, the culture has changed a lot.
Okay.
Because when I first joined and I said I'm a theoretical neuroscientist, people would look at me like say, "What does that mean?" And where is your lab? You must have a
Yeah.
lab hidden somewhere that we haven't seen, because it was not a proper branch of neuroscience to be a
Yeah.
theoretical neuroscientist. But
Mm.
now it is.
Yeah.
Now
So
you
because
have
because
conferences that are theoretical and computational neuroscience. You see job announcements where say
mm.
we are looking for the theoretical computational neuroscientist. So it's become a
Mm.
perfectly legal and recognized activity.
Mm. Because I think if you sort of, I mean, uh, you were not teaching then in a medical school, because I think that's often the requirement, at least in if you look at medical position in the medical department, requires teaching to medical students, and that's not so easy to
No,
do,
no,
right?
that's not. But our medical school, and I think every medical school has a few what are called basic science departments.
Yeah.
And the faculty in these basic science departments, almost all of us are PhDs. We are not MDs.
Mm.
So we are not really asked to teach the medical students.
No.
I've been asked a couple of times to teach because they know I'm a physicist, to teach
Yeah.
about blood pressure.
Yeah.
What
Yeah.
does it mean to
Yeah.
have blood pressure, and
Yeah.
how do we measure it, and why
Yeah.
does it work the way we measure it?
Yeah.
But except for that, I don't have any interaction with
Mm.
medical students.
Mm.
We teach in graduate programs. We teach in my department, which is the neuroscience department. We teach in the neuroscience PhD program, the
Mm.
biomedical engineering PhD program. I've taught
Mm.
couple of courses in physics and applied math of the
Mm.
fundamentals, of computational neuroscience. Um, but we don't have the same teaching obligation
No.
or the same
Mm.
teaching load as other colleagues in the physics or mathematics department, because they also teach undergraduates. We
Mm.
have no contact with undergraduates.
No.
We only
Yeah.
teach graduate students.
Cool. Okay, so now we have after this nice introduction, I think we're going to talk about manifolds, and I think and the use of that in order to understand what the motor cortex is doing. And so I guess it started with this. Well, like there was this. I've been reading this your 2017 paper It's like this neuron
The neural
neural paper.
paper with
Yeah,
Juan Diego and Matt Perich.
yeah,
Yes.
neural manifolds for the control of movement. So this is sort of like I like to yeah. So this is sort of like a main topic of this podcast, and uh, I just want to go a little bit back, sort of into so what I mean. If you sort of think about like the Jubel and Weasel, what they found out the visual system with single unit recordings, and people tried, obviously researchers tried to do the same thing for motor cortex and look for representations of motor movement, like in the 50s and 60s. And but that was not so easy in the motor cortex. Was it? It was more messy.
Well, if you look back at the work of Georgopoulos in the 80s,
Mm.
he did find specialized neurons. So let me go back to a task that is like the pendulum in physics, like the harmonic oscillator for
Okay.
motor control. There is a very prototypical task that almost everybody uses, what is called a center out task. So let me
Mm.
tell you what the task is. There is a dot in the center, and it's surrounded by 8 dots in a circle. So you
Mm.
are, in the simplest case, you're supposed to touch the center. That starts a trial. Then one of the 8 lights,
Mm.
8 circles lights up, and it
Mm.
stays light up. So it's not a memory task. You don't have to remember it. It stays light up. But you have to wait for the go signal. When you get the go signal, you go there, you touch it, and come back.
Mm.
And maybe you do it on the
So
screen.
you move the point the finger on the screen or the monkey.
Yeah.
Yeah.
Or maybe you have a little lever here, a
Ah.
manipulandum, which is in
Mm.
2 dimensions,
Like
and that
a
moves a dot in the screen.
like a
And the dot
joystick.
in the screen follows what you're doing with your hand in this 2 dimension. And that's typically the way it's done with the monkey.
Yeah.
So this is called a center out task. You can do many trials. The monkeys learn it. They do it in a very stereotypical manner. Humans also do
Mm.
it. And it's interesting because it gives us 8 directions of motion.
Mm.
And Georgopoulos used this task in the 80s when you could only record one neuron at a time. So this is the equivalent of Hubel and Wiesel, so one neuron at a time.
Mm.
And they found in motor cortex that about not all the neurons, but about a third of the neurons had what they call direction selectivity,
Mm.
in the sense that if you move in this direction, the neuron fired a lot. In
Mm.
the interval just before the go signal, when you are in motion preparation, and during the actual going to that
Mm.
target.
Mm.
And but now, if the same neuron, when you do the opposite movement,
Mm.
not the preferred direction, but the anti-preferred direction, actually there is a suppression of firing. And in the two perpendicular directions, there is almost no effect.
Mm.
So now you have a tuning curve for that neuron. It's a tuning curve with only 8 points because you're not varying direction in a continuous manner. You only have these 8 possible directions. But one of them is the preferred direction, and then it goes away, and there
Mm.
is a background level, so it is above background and below background in the opposite direction. So
Mm.
Georgopoulos suggested fitting this to a cosine curve.
Mm.
So this cosine curve has only 3 parameters. The theta I, if this is neuron I, the theta I, which is the preferred direction for that neuron, an amplitude that he called A sub I, which is the difference between the maximum and the minimum firing rate. That's the amplitude of modulation. And then BI, which is the background, the mean
Mm.
firing rate, or the background firing rate of that neuron, BI. So with these 3 parameters, BI, background, A sub I, amplitude of modulation, and theta I, preferred direction, they were able to fit all these direction selective neurons.
Yeah. Mm.
So this we knew from the work of the 80s that if you look at the single neuron level, you would find neurons in primary motor cortex that encoded for direction of motion. Then there was an avenue that was also single neuron avenue that was not so productive, which was people who said, look, we don't control the direction of motion. We control the muscles,
Mm.
the neural signals from motor cortex go to neurons in the spinal cord, which are called motor neurons, and the motor neurons go to the muscles. So then these neurons in the primary motor cortex are two steps away, two synapses away from controlling muscle contraction. And it's the muscle contraction that allows me to move the arm in this direction versus that direction. So they said perhaps what motor cortex is encoding for is actual patterns of muscle activation. And as a consequence of that, we see the kinematics in this two-dimensional plane. But maybe the fundamental map, the fundamental decoding is from neural activity to muscles. And they tried very hard to find an equivalent muscle representation in primary motor cortex, something that would be so clean as this direction of motion. But that was never found at the level of single neurons. So that is perhaps what you're thinking of when you say that it was not a productive avenue to look at single neuron encoding. But the direction of motion was a very important aspect of the way people thought about motor cortex. And it's, in my mind, it's equivalent to the direction selectivity neurons that were finding vision, the Hubel-Visser experiments that you were reminding us of earlier.
Yeah.
So there we were. Then now we started doing the same task many years later when we have now the ability to record simultaneously. So we can implant an electrode array. So if you're moving this arm, we implanted, of course, in the contralateral area of motor cortex. Motor cortex, you can map a homunculus. So you can say this is the feet area, the arm area, the face area. So we put it in the arm area. This electrode array is 10 by 10. So it has 100 electrodes. It's about 4 millimeters. So about 400 microns between adjacent electrodes. So you make a small hole very small hole on the bone and the cranium, and you just implant this electrode
So
array.
are these the neuropixel probes, or this is
No,
another?
these are called multi-electrode arrays. The
Okay.
neuropixels come later, and the neuropixels allow for more recording.
Okay.
These
But it's
electrode arrays,
this
being 10 by 10, only had 100 electrodes, and we could record of the order of 100 neurons. With
100 or 500, 100 of 100
100
neurons.
neurons.
Yeah.
Yeah, 10 by 10, 100 neurons.
Yeah.
With neuropixels, you can record several hundred and up to 1,000 neurons.
Okay.
As you can put many neuropixels
Yeah.
simultaneously, and you can record several areas
Yeah.
simultaneously. But typically, several hundreds in
Yeah.
each area.
But the experiments you referred to are maybe like done in like 20, 15 years ago or something, like
So
before
the experiments that we reported in this neuron paper, and that triggered this whole idea of manifolds, were done with multi-electrode arrays, and we were, yes, about 15, 20 years ago. So
Cool.
that's what triggered the idea of manifolds.
Yeah. So okay, so then you had all these recordings of say 100 neurons. Then just take that as a number from across the motor cortex when they did this center out
Yes.
thing.
So
S-
we have neural activity simultaneously recorded, let's say 100 neurons, and we have the trajectory of the dot on the screen. We have X and Y components, X and Y position and X and Y velocity
yeah, of the arm or whatever of the
of
hand
the dot on the screen.
of the dot of what?
The
Oh
dot
yeah,
on
the
the,
dot. Okay.
which is being controlled by the arm, either by
Okay.
because
Yeah.
you touch it
Okay.
or because you have a manipulator.
Okay. Yeah.
So we had this neural to behavior
Mm-hmm.
data, and we began to create decoders that
Mm-hmm.
implemented that. But before that, we began to analyze the data, and we were looking at the data. And so when you look at the neural data independent of the target. You can do dimensionality reduction in a very simple manner. You do principal component analysis.
But maybe start with this is an important point. So, say if you have these 100 neurons, and then
Yes,
you can plot these 100, say 100 firing rates or something, like some one number from for each of these neurons in a 100 dimensional space, which is a high
exactly.
dimensional space. And then you want to reduce this data into doing some, yeah.
Exactly. So that's the neural space is 100 dimensions. Each axis represents the firing rate of an individual neuron.
And then you do some
So what
reload.
we
Yeah.
started doing, which also was what the group of Krishna Shenoy at Stanford started doing, was we took a 300 millisecond interval around the go signal, and we computed the firing rate for each neuron in that interval. So for that trial. So that gave us 1 point in the neural space because we compute the firing rate for neuron 1, neuron 2, neuron 3. Only one firing rate. We didn't follow the trajectory. We just said, let's take one measure um, a little bit before the go signal, about 50 milliseconds before the go signal, or 100 milliseconds, and then 200 milliseconds once the movement has started. So we put all these points in a very high dimensional space. But now, of course, we cannot visualize a 100-dimensional space. So we started by doing, let's say, well, let's pick three neurons at random and put these points in this three-dimensional space, neuron 40, neuron 70, neuron 8. We put each point, and then we color the targets and we color the points according to the target.
Okay.
So this point corresponded to a trial, and each trial was to a different target. The targets were chosen at random for each one of these reaches. And this plot was totally disappointing. The colors did not cluster. Every point was surrounded by points of a completely different color. So the location in this
was just
artificially constructed three-dimensional neural space did not give any
so that was really a mess.
about target identity.
Yeah.
So we said, well, we must be doing. Then we went back to Georgopoulos and we said, well, let's imagine that I have an ensemble of 100 neurons. Each one of them is a Georgopoulos neuron. So each one of them has preferred direction, amplitude of modulation, background. Okay. And let's assume that they are not connected. It's like in physics, like an ideal gas of non-interacting particles. So non-interacting neurons. But each one of them is responding with its own tuning curve to the direction of motion. What would the neural activity look like? And then the neural activity looks like a ring where you go, if you again color according to target, you keep on changing colors in this ring. So we said this ring is a low-dimensional object. It's a ring living in a 100-dimensional space. If we do dimensionality reduction in a smart way, we should be able to see it.
Yeah.
So where do you start? You start by doing principal component analysis, right? So you do principal component analysis. The variance increases very, very slowly. So if you want to account for 80 or 90% of the variance, you have to keep more than 20 dimensions. That was not very useful.
20 of the 100.
20 out of 100. So again, it's still not very useful for visualization. So we said, okay, let's take the leading three components, project all the data. Now, this is all the data. Again, when you do the principal component analysis, you have no target information. This is every point. You have a cloud of points in this neural space. You take the whole cloud of points to do dimensionality reduction. You project all these points in this three-dimensional space spanned by the three leading principal components, and then you color them. And once you color them, it was beautiful because it clustered. You had 8 clusters according to the 8 targets. And what was totally amazing was that if you look at the order in which the colors appeared, it was the same order in which we had colored the targets in the physical space. So this was a totally abstract neural representation of the task and of the physical organization of the task in the outer space. This was totally amazing. And we were playing with it and trying to understand, and we got scooped because Krishna Shenoy's group did exactly the same thing. showing using factors analysis, which is
Mm,
just a more sophisticated version of principal component analysis. And they showed the data in the three-dimensional space, and they showed exactly what we had. They
mm,
showed the 8 clusters colored, and
mm,
when you look at the color of the clusters and the way you color the targets in real space,
mhm,
it's a one-to-one correspondence in terms of the order of this kind of circle that they span. But this was a very important result because it showed that this direction selectivity made sense not only at the level of individual neurons, like Georgopoulos had said in the 80s, but at the population level,
mm,
which is what the multi-electrode arrays allowed us to
mm,
monitor, allow us to record 100 neurons simultaneously. So
mhm,
this really was the beginning of the manifold story.
mm,
It was the observation that there was a low dimensional, 3 dimensions were sufficient. And then there was beautiful work by my colleague Surya Ganguly, also at Stanford later on, where he and his colleague Gao argued that the dimensionality of the manifold was proxy for the complexity of the task.
mm.
That if the task is very simple, you expect a low dimensional representation, which is what we found. We found 3 dimensions were great. Even in 2 dimensions, you would see the clusters, although they were not so well defined. But three
Because
dimensions,
this center outreach thing task was so
yes.
simple.
The task is essentially a 2 dimensional task.
Yeah. Mm,
So it's not
yeah.
surprising that the
Yeah.
complexity of the task
Mm,
is, you can say, it's 2 dimensional, and then maybe the third dimension has to do with the ordering of
yeah.
the targets of the
Yeah.
circle. But that's exactly the representation that we found, really.
Mm, mm,
But of course, if you're playing a piano sonata, I would expect that
yeah.
I would find a low dimensional manifold, but not 3 dimensional,
No.
like.
Mm, mm, yeah.
But the thing to keep in mind, Gaut, is we were recording 100 neurons. But if I do a very simple reach, like if I touch the screen with my arm, of the order of 1 million neurons in primary motor cortex get modulated by that simple reach. So if I wanted to really report the full involvement of the neural space, I would have to represent a 1 million dimensional neural space. Of course, I can only record 100. So even with a neuropixel, if I could record 1,000 with a neuropixel, it would still be an extreme case of subsampling.
Mm, mm,
And yet, that subsampling is ample enough to allow me to find the manifold,
yeah.
because the manifold is very low dimensional,
Yeah.
even when compared to the dimensionality of the empirical neural space, which is the number of neurons that I can record, which is much smaller than the dimensionality of the true neural space,
Mm,
which is the number of neurons that are actually commodulated by
yeah.
this simple task.
Mm,
So we have a mother neural space, which is the real, very high dimensional, an empirical neural space, which is what we can record, and then the manifold, which
yeah.
is so low dimensional that we can find it even in the empirical neural
Yeah.
space.
Yeah. Cool. So then, of course, one immediate consequence of that is that if you have very few recordings from neurons, you cannot really understand very complicated behavior. I mean, there's
Exactly.
sort of like the low dimensional whatever neural activity must be lower than the number of, or cannot be higher than the number of recordings.
Exactly.
Yeah,
The low dimension, but
but that's
everything that
maybe
we
never the problem.
everything that we have found so far. So now we have there is always a criticism, like it is going back to Hubel and Wiesel, that this is not natural neuroscience. This is
Oh,
not neuroethology, because you are examining a very artificial task in a
okay.
laboratory setting,
Mm,
which is not the task that the organism performs in the real world. It doesn't belong to the set of tasks that the
mm,
organism performs in the real world, which is the task that we have evolved
mm.
to
I
be
see.
able to perform.
Uh,
And so your sampling from the behavioral point of view is a very artificial sampling, because you are sampling behavior in a in an environment, in a setting which is very, very far removed from the actual setting
Mm.
of the
Okay.
natural behavior. So one thing that we have advanced is now we have constructed a cage in which the monkey can move, and the cage has is a rich environment, so he can grab trees, he can climb, he can. There are several things,
Yeah.
and we can record for an hour or so. During
Mm.
this hour, the behavior changes a lot. So
Mm.
we are sampling many different activities. And yet, when we look at the neural activity during that whole hour, the dimension is 30, maybe
Okay.
40. It's not even 100.
Mm. I see.
So it's certainly not three, but
Uh,
we still have this strong belief that they are low dimensional manifolds associated with specific tasks,
mhm.
and that your attention or decisions that come from the prefrontal cortex put you into the right manifold. And then
Ah.
in that manifold, you execute the dynamics, the trajectories corresponding to that task, but that these trajectories are can be studied as low dimensional dynamical systems because
Mhm.
during the task execution, the activity, the neural activity, the collective neural activity is confined to the corresponding manifold.
Ah. So okay. So you have this. Okay. So now I have this say during one activity, or so okay. So then you have this low dimensional manifold, maybe like three, 4 dimensions or whatever. And while you're doing the task which has that manifold, the dynamics can be described by some kind of well, the behavior within this low
By
dimensional manifold.
trajectories, neural trajectories within the manifold, and my
Yeah.
colleague Tatiana Engel at Princeton is advancing really this. Let me make an aside. We have developed and tested and recommended very specific methods for determining the dimensionality of these manifolds.
Okay.
If they are flat, they are like hyperplanes, or if they are curved, if they are non-linear, which they typically are, because they
Mm.
are made up of neural activity and the neurons are non-linear, they are connected by synapses that are non-linear. It will be very surprising to.
But and now I'm a little confused. So because a circle, which is a manifold in the 2 dimensions, that is that curved, but it's not curved in your sense.
That's okay. So let me cite another work that is very important. There is a
Ah.
beautiful paper, but Ostojic and Hasayeri, where they discuss the difference between intrinsic and embedding dimensions. So
Ah.
if I look at this, it's a
Yeah.
circle, right?
Mm.
So the intrinsic dimension is one. I only need one variable to tell you where I am in the
Mm.
circle.
Mm.
But if I wanted to embed it,
Sarah is showing a loop here on the for the
I'm
listeners
showing
who's
you a
not
loop.
watching. Yeah, showing
Yeah,
a
I'm
loop
showing you a loop.
with
Sorry.
some kind of yeah,
Yeah, I'm showing you a loop.
lanyard or something. That's fine. Yeah.
So
Okay.
there is only one variable that tells me where I am in the loop, right?
Mm.
But let's say I wanted that's the intrinsic dimension of this object. So let me now try to embed it in an Euclidean space. I need to put it on my table.
Mm. Yeah.
So the embedding dimension is two,
Yeah. Yeah. Because you can put it
although
on the
the
table.
intrinsic
Mm.
dimension is one. And the difference between those is because the object is nonlinear.
Okay. Yeah. I
Because
see.
if I only had one line,
Mm. Yeah. Yeah.
the intrinsic dimension would be one, and the embedding dimension would also be one.
Okay. Yeah.
So imagine, for instance, the surface of the Earth.
Mm.
The intrinsic dimension is two,
Mm.
but the
Yeah.
embedding dimension is three
Yeah.
because
Mm.
it's not a flat surface.
Mm. Okay. Yeah.
And so we have linear methods and methods for estimating the dimensionality of linear manifolds and methods for estimating the dimensionality of nonlinear manifolds.
Okay.
With these methods are very good, but we have compared them in in control data
So
sets where
just so the non-linear. So then you talk about non-linear in terms of the embedding dimension, or
no, the nonlinearity comes from. So let me go back to this loop.
back to the loop.
Let's go back to the loop and let's say I
Yeah,
put it on the table.
yeah,
And now I take a point in that loop and I pinch it upwards.
okay,
I don't know how to show you the table and the loop at the same. But
that's
so
fine. Yeah,
the loop is on the table and I take one point and I pinch it upwards.
okay,
Okay. I go like this, I go
yeah,
up and down, and I continue the loop. The intrinsic dimension is still one,
mm,
but now the embedding dimension is three
yeah,
because
because
it's no
you're
longer flat on the table. I need the z axis to
mm,
be able to go up and down. Now imagine this is a neural manifold embedded in a 100-dimensional space.
mm,
I still have 97 dimensions in which I can make these little protuberances,
yeah,
and come back. So I can increase the embedding dimension. I can make it 4, 5, 6, but the intrinsic dimension always remains one.
okay, yeah,
However, every time I make one of these things, I
uh,
make the manifold more nonlinear
okay,
because I'm locally increasing the curvature
okay,
by
yeah,
making. So we propose, it's not a theorem, but we propose that the difference between the embedding dimension and the intrinsic dimension, be it the difference or the ratio, can be considered a nonlinearity index.
okay,
It's a proxy
yeah,
for the nonlinearity of the object.
mm, mm,
The more nonlinear the object, the highest the difference between its intrinsic dimension and the embedding dimension.
yeah, the smallest embedding dimension, then maybe.
The embedding dimension is the dimension of the smallest Euclidean space
Yeah,
in which I can put the full object without
yeah,
losing any of its features.
yeah, cool.
So this is what Ostojic and Hasayeri define as the embedding dimension. It's a
Okay.
beautiful paper where they make the distinction between embedding
Mm.
dimension and intrinsic
Yeah,
dimension.
I'll find the link to it or link it up to the homepage of the episode.
Yeah, it's a beautiful paper. So and we have, as I said, we have proposed and tested and made available a very good set of tools for determining these dimensionalities. But my colleague Tatiana Engel at Princeton is now pushing this further because what she's trying to do is quantify. Of course, quantifying the linear manifolds is very easy, right? It's a hyperplane. You just find the basis. You can use principal component or factors analysis or probabilistic PCA, but you find a few vectors that are linearly independent. You can make it orthogonal even, unit length, and they give you a basis. And once you have a basis, every point in the hyperplane can be written as a linear combination of that basis. So the basis gives you a full description of the linear manifold. When the manifold is nonlinear, if it's curved like a piece of paper like this,
Yeah,
in every point I can still construct a basis, but now I
yeah,
have to rotate the basis if I
yeah,
move on the manifold, right?
yeah,
So that problem of getting a geometric description of the manifold when it's nonlinear is more complicated.
yeah,
And then, as I said, if the executive order from prefrontal or wherever you're making a decision says, now I'm going to brush my teeth, that's the task. Motor cortex needs to go to the manifold that corresponds to that task. And in that manifold, there will be a trajectory that corresponds to the movement of brushing your teeth. But that trajectory will be confined to a low dimensional manifold. So the problem has two aspects. One of them is characterizing the nonlinear manifold and finding the low dimensional dynamical system that describes the trajectory in that manifold.
ah.
And that's a very open problem in which people like
So,
Tatiana Engel are making progress.
so you're sort of saying that, like, well, if you're brushing your teeth, that has a separate little manifold
Yeah.
for that.
So,
Yeah.
This is the conceptual picture that we have, that every time you learn a task,
Mm,
you acquire a manifold in your motor cortex.
mm,
And this is a very beautiful picture because the manifolds are low dimensional and wiggly. They are not flat,
mm,
But imagine this enormous neural space, has
mm,
millions of dimensions. I put a low dimensional wiggly manifold here
mm,
corresponding to task A. And
mm,
then I put another wiggly low dimensional manifold there corresponding to task B.
mm,
I don't run into a capacity problem very easily. And these manifolds do not interfere with each other because they are low dimensional.
mm. So there's plenty of room.
There is plenty of room. You learn
Mm,
one piano sonata, now you can learn
yeah.
another piano sonata.
Uh,
Moreover, you can also facilitate learning
uh,
because of some of the directions in this manifold can be used to learn the second piano sonata.
mm,
Then there will be some directions in common between these two
okay.
manifolds. So the
Oh,
learning facilitation can be understood as borrowing some of the modes that are part of manifold A
uh,
to begin to create manifold B.
oh, ooh.
And they are
Yo.
very beautiful learning experiments by my colleague Aaron Batista in
Mm,
Pittsburgh that show that explicitly
ah,
that you can reuse. We call them modes because each direction
mm,
is a direction in neural space, and each direction is a linear combination of many neurons.
mm,
So they are definitely not single neuron descriptions.
mm,
Every mode projects itself onto a very, very large number of neurons,
yeah.
requires the concerted activity, the concerted covariance of many neurons to stay in that direction.
Ah,
So what you do is you learn these modes, and when you are going to recombine modes that you already know, the learning is very fast. But
ah,
when you need to acquire a new mode in a
mm,
new direction that was not acquired before, then the learning becomes very laborious again.
ah,
And this
ah.
is what Aaron Batista showed in a
Because what?
beautiful
Hmm.
executed example. Again,
S-
using the centered out task, which, as I said, is kind
So,
of the
so,
canonical task of motor
so,
control.
so the way to think about it is that sort of like you can think of your like movement in or the dynamics in this manifold is sort of like a consists of a set of neural modes that are activated. Some says pre-existing neural modes that are activated.
Exactly.
Yeah.
Exactly. And this is what people call the latent variables. The
Mm,
latent variables are the dynamical evolution of the level of activation in each one of these neural modes. Those
mm,
are the latent variables. And in my view, the latent variables are the building blocks of activity and behavior. It's not the
mm,
individual neurons.
mm, mm,
Maybe there is a few of them, but it's not a few neurons. Each one of
mm,
them involves a pattern
mm.
of activity of many
Yeah.
neurons. So it's a collective a property, a mode, or a
So,
latent variable.
cool. So what about sort of like then if you have this, I mean, spontaneous activity and like some kind of stimulus evoked activity, they use the same modes or
Um,
like,
so
yeah.
that's a very good question. I think a spontaneous activity does not necessarily use the same modes. I think
Uh,
a spontaneous activity is exploring space between manifolds,
okay.
space that is not associated with a given task. I
Uh,
think the man, I in my this is again not a mathematical proof, but my the intuition that I have developed about this geometrical organization of the
mm,
manifolds is that the manifolds are task specific. For instance, why do athletes and musicians keep on rehearsing and keep on practicing?
yeah.
They say that is to stabilize or to maintain a muscle memory.
Mm,
But the muscles don't have any memory. The
mm,
muscles are just elastic fibers
mm,
that
mm,
that are contract according to neural commands. They don't have memory. The memory is the manifold, is the
mm,
neural manifold. And what you do when you rehearse and when you practice is you stabilize the manifold.
mm. Because
There is a
the
task associated
yeah.
manifold. Is a manifold specific for that task. And every time you serve, you go to the serve manifold. And it's very idiosyncratic and it's very stable. Like if I see eh, Nadal serving, I know it's Nadal, even if the figure is obscure, right?
Mm.
There is a way in which he serves.
Yeah.
The
Yeah.
behavior is very stereotyped. In the same way in which the center out task, once the monkeys acquire it, if you look at the trajectories in this XY space, you find that Vx and Vy for a given direction of the target, we have monkeys that have been doing this task for almost 3 years in the lab.
Mm.
Not
Uh-huh.
all the time. They come and they do that
Right.
task, or they do other. So
Yeah.
we can compare day one with day 200, with day 400,
Yeah.
with day 700. The trajectories are very stereotyped
Mm. I see.
because the monkey has acquired the manifold
Yeah.
and it rehearses the manifold. And in the manifold, the dynamics are very stereotyped
But
for
then
that particular task.
over a 2 year period, whatever, then it's like some neurons die, right? Then or some, or presumably, right? So the individual neurons may change.
Exactly. And that's the advantage of having a collective representation that is very robust
Yeah.
as compared to having a grandmother cell that the day
Yeah.
the
Yeah.
cell dies, you don't recognize your grandmother anymore, right?
Hmm.
So
Yeah.
it's not associated with a few neurons, it's associated with many
Hmm.
hundreds and thousands of neurons. So if
Hmm.
a few die, the mode, the direction in neural space
Hmm.
still retains enough of its identity.
And then there's some kind of synaptic plasticity presumably involved because it's really these the the manifolds and like these different neural modes at the biophysical level, they have to do with how which neurons are connected to which, right? And
Exactly.
yeah, so
Exactly.
this is something it has to do with the network. So
Exactly.
if you want to have change, if you want to change a participant or a member of a particular like neural mode, or then you need some kind of plasticity for the newcomer or something.
I completely agree
Yeah.
that this whole thing, the organization in manifolds has to be a reflection of network connectivity.
Mhm.
And then you can ask yourself, well, what aspects of the network connectivity will allow me to develop low dimensional manifolds?
Yeah.
There is a beautiful example, and the data comes from the lab of Mark Churchland at Columbia University, again using the center out task.
Mhm.
But they were monitoring not only the location of the point in XY space, but also the activity of some muscles. So they had muscle cups, and
Mhm.
there were about 6 muscles or 8, I don't remember exactly, that they were monitoring. And David Susilo, who is a co-author in this paper, did the following. He took a recurrent neural network
Mhm.
and it had 8 possible inputs.
Mhm.
The inputs were 1, 0, 0, 0, 0, 1, 0, 0, 0, just telling this trial is to one
Yeah.
of the 8 targets.
Mhm.
And the output, which was made with, I think he was monitoring 4 muscles, so 4 readout neurons, was supposed to be a signal as a function of time that was representative of the activity of each one of those muscles being recorded.
Mhm.
At the beginning, he wires the network at random. It's not a trained network.
Mhm.
Of course, the outputs don't follow at all the activity of
Mhm.
the muscles, but he looks at the dynamics of the network. And the dynamics of the network is high dimensional. He cannot reduce it.
Mhm. Okay.
Now he trains the network to produce these
Mhm.
correct
Yeah.
functions of time will represent the activity, the recorded activity of these 4 muscles. And then he looks at the dynamics, he studies the dynamics of the train network. The
Mhm.
train network shows low dimensional
Ah.
dynamics.
Yeah. Yeah.
So it's absolutely what this is a demonstration, it's not a proof, but
Yeah.
it follows exactly the intuition that you were outlining before. That is the connectivity. When you learn the task, the connectivity of the train network has created a low dimensional manifold.
Ah.
And then the conceptual question is what properties of the connectivity result in low-dimensional dynamics.
Mm.
And Ostojic at l'École Normale in Paris, Sredin Ostojic, and his team have proposed a very interesting idea, which is that if the connectivity is low rank, then it
Okay.
will be associated with low rank dynamics. So
Okay.
I can make an outer product of three vectors with three vectors, and
Mm.
the connectivity is full. Everybody's got, it looks like full connectivity. The connectivity
Okay.
matrix
Uh,
doesn't have zeros, it's not
uh,
sparse, but it
uh,
is low rank.
uh,
And then it results in low rank dynamics.
okay. Yeah.
Now, and he has shown many examples of that. The question is, so in some sense, I think that what he has shown is that this is a sufficient condition,
Uh,
that low rank connectivity is sufficient for the emergence of manifolds, low dimensional manifolds. But
uh,
I don't know if it's a necessary condition.
no.
I don't know if there are not other mechanisms, like the Susilo case,
Uh,
where the train network, the connectivity was not low rank, and yet it exhibited low dimensional dynamics. So
yeah.
I think it's a very interesting question in dynamical systems, is what if I
Uh,
have many degrees of freedom connected in a certain way, what properties of the connectivity matrix will guarantee that the dynamics is confined to a low dimensional manifold,
uh,
although the state space is very high, which is like the neural
uh,
space in our case,
yeah.
is very, very high dimensional.
Yeah, maybe it's sort of maybe it's like I know this is just thinking out loud, but you have this if you have a rather low dimensional problem, if you make a low dimensional solution that's more robust and don't make it more complicated than you need to, sort of. I mean, I don't know. It
If you
just
have a low dimensional problem, you're saying, why is it living in a very high dimensional
yeah,
space?
it just seems like if you have some like if you have a relatively simple problem, I mean, it just seems like a low rank solution is more robust to noise
Oh,
or
I see. I see.
yeah,
Yeah.
I
No,
don't know.
the
I don't
question
know.
is in the low rank connectivities, how now you promote this picture to
Mm.
being able to embed several manifolds in the neural
Yeah,
space, not just one. Yeah.
yeah. Mm. Cool. So I mean this because one thing you show this that is so long lasting because I was thinking if you're sort of like biking, for example, is something you never forget, right? Is
Right.
that maybe because it's this sort of this our biking manifold was which was sort of constructed well when we were kids and under some suffering and painful falls is still around with us today.
I don't know. Maybe it has to do with the time history of when you embedded these different manifolds and
Mm.
created them, because the way retrograde amnesia works, with
Mm.
people who have senility, for instance.
Yeah.
You forget the most recent events,
Mm.
but
Yeah.
you still remember some very, very long in
Yeah.
the past events.
Mm.
So I don't know if it has to do with the fact that you brought up bicycling. We all learn to bicycle when we are very young.
Mm. Yeah.
And if you learn to ski when you are 40 or 50, not when you were very young, would you
Yeah.
forget it more easily than a
Yeah.
person who has learned it? But I don't know. I'm just speculating whether
Mm.
it's related to this different embedding of memories that we embedded when the brain was incredibly plastic,
Mm.
as opposed to memories that we embedded later when
Mm.
plasticity was not so big as it is, before
Mm.
adolescence, before puberty.
Mm. So I mean, now, so this, I mean, what we talked about so far is essentially this, essentially like a statistical analysis, a variation of statistical analysis, and an alternative is sort of to try to make, or another way to try to model it is by sort of making more like mechanistic models of say a motor cortex with real neurons, where integrated fire neurons, some kind of thing, and has
Right.
has has. I mean, you would maybe think if like a mechanistic model of motor cortex, if it's successful, then it should be able to exhibit this manifold behavior and I'm not quite sure if that has been explored or if it's
Yeah. Well, I would say that the Susilo simulation is such a model. The simulation
Uh,
where he trained the network to do something that motor cortex
that's
does,
true.
which is to produce these particular patterns of muscle activation
Mm.
in order to be able to implement. These were taken during the execution of these eight
But
targets, central
but
targets.
presumably that was with some, I don't know, with some kind of rather generic network structure. It didn't sort of take into account the real neurons of the motor cortex and the real connectivity of the motor cortex, and so this was,
Right. This was trained in the way we train the recurrent network. It's an
yeah,
artificial neural network.
yeah. So it's
The
like a different type,
mechanistic,
yeah.
do you mean more realistic neurons or more
Yeah,
realistic?
more realistic neurons and looking at the connectivity which is actually there with like
Yeah,
the input from layer 4 to layer 2, 3, and
I
so on. I
see.
mean,
I
it will
see what
be,
you mean. No,
yeah.
I don't know of any efforts
Hmm.
that start that way and try to find manifolds. I
No,
don't know. No,
because at some point you would like these kind of models to meet, right? That would be the,
that's right. But
yeah,
sometimes the extreme of this class of models is the blue brain. And
yeah.
I'm very skeptical of that because I don't know if you have heard this story. I like to tell this story sometimes when I talk to people who are not modelers. It's a short story by Borges. It's
Mm,
an apocryphal story, but he has a book of invented stories, apocryphal stories.
yeah.
And this is a short story, it's half a page, and it's called On Exactitude in Science.
Mm,
And in this story, he talks about a civilization of cartographers who wanted to make maps, and they
mm,
took great pride on the precision of their maps.
yeah.
So, in order to be more and more precise and incorporate more and more realistic details, they
Mm,
started making bigger and bigger and bigger maps.
mm,
So, first they had a map of the empire that was as big as a city block.
yeah.
Then, after many generations, they had a map of the empire that was as big as the big city that was the capital of the empire.
Mm,
And then, after many, many more generations of working, they had a map of the empire that was as big as the empire.
yeah. Yeah.
So,
Yeah.
that was the end of their efforts. This map was totally useless.
Mm.
They completely abandoned cartography. And
Yeah.
now, when you walk through the empire, you can see pieces of paper that
Yeah.
are superimposed
Yeah, that's
that have
also,
exactly the same features as the ground underneath.
no, that is true. But I was sort of on the behalf of this very eager cartography.
So,
This was on the internet. This could have been used to get simpler models, right? It's a fantastic. It's sort of like a test animal. I mean, I think some
right,
of
it
these very
is.
complicated models is sort of like a
But the
test
question
and.
is, if you have a map of the brain that is as big as the brain,
Mm,
what are you going to what you can do? Actually,
mm,
I should be careful. What you
mm,
can do in a model that you cannot do in the brain is interventions.
mm.
You can do arbitrary interventions in the model that you cannot
Exactly.
do in the real brain, and that
Yeah.
is can be very powerful to understand mechanisms.
Yeah.
But the model that you're suggesting, where we try to grab some details of some of the neurons and some details of some of the circuitry,
Mm,
I would have a very hard time for this question of manifolds and separating which are the relevant features that I need to incorporate and
mm,
which are the irrelevant features that I can leave out.
mm,
Because that selection is extremely dependent on the question that
on the
you're
question.
asking, of course.
But if you had that model, you could.
Question about existence of low dimensional manifolds. For that question,
Uh,
I do not know which are the
but
neural features that are relevant and which are the connectivity features that are
but
relevant.
this you could find out with such a model because you could try to look for manifolds with one parameter turn off and with one parameter turn on, and it
Yeah,
would be like a fantastic test animal as I think of it. But I
no,
agree, it
it
doesn't.
is. It
Yeah.
is. Once you have the model, with my colleagues Richard Gast and Kennedy, who are used to be at Northwestern and both at Scripps, we started studying recurrent networks in which you introduce heterogeneity in the
Mm,
neurons. So you, for instance, can study an excitatory inhibitory two subpopulations, which not only the excitatory is different from the inhibitory, but there is heterogeneity within the excitatory population and within the inhibitory population. For instance, we studied heterogeneity in the threshold, in the firing threshold, using quadratic integrate and fire neurons. So now I can do in the model something that I cannot do in the system, which is make the inhibitory population heterogeneous, but not the excitatory,
Exactly.
and see what is the effect of the inhibitory heterogeneity on the homogeneous excitatory population, and vice versa.
Yeah.
It is not something that I can do in the real system. I cannot make one of the subpopulations heterogeneous and the other subpopulation
No.
homogeneous.
No.
So that's the power of a good model, is it allows you to do interventions that you cannot do in the
Yeah.
real system.
That's true. And of course, also if you at some point want to maybe develop drugs that should help for like movement disorders,
Exactly.
then you have to be at the level of biophysics, or
Exactly. Then you can ask exactly a
then you
similar.
need these kinds of things. So anyway, so but
Yeah.
this neuro, now so far you've talked about neural manifolds in electrophysiological data with many recording spike action potentials from spikes from many neurons. What about, I mean, optical recordings? Then you can sort of it, not in monkey maybe, but in mice you can really get many more neurons, right?
Right.
So
Right.
so
So
then it allows for like so yeah, of course it has a poorer time resolution, but still you should be able to see similar things.
no, I mean you can use Neuralink in mice, in rodents in general, and then you can, you have this exactly the same time resolution. You see individual spikes, so
Mm.
you have the same time resolutions as we see with multi-electrodes arrays. These are neurophysiological
Yeah.
recordings. Um, you can what allows it allows you to, well, not again, one finds low dimensional manifolds in individual regions, but now Neuralink, for instance, allows you to study interactions across regions.
Mm.
And so, for instance, I collaborate with Andrew Meady and Northwestern in an experiment which is a self-initiation of movement. So it's a decision to move that is not cued externally.
Mm.
So this is a rat climbing one of these circular, typical
Okay.
rodent
Yeah.
steps, and the rat decides when to climb and when not to climb. It's
Mm.
not that in response to an auditory stimulus or in response to a light. It's not response to a
Mm.
cue. And we ask ourselves, where is this decision to move initiated? Is there, it's not an accumulation of evidence, it's maybe an accumulation of intent until you say, oh, I should move, I should move. Okay, I will move. And so we record simultaneously on sensory areas, on motor areas, on striatum, and in areas that are equivalent to prefrontal cortex.
Mm.
So we not only we can find the latent variables, the low dimensional manifolds in each one of these areas, but we can now try to describe the interaction across areas, also latent to latent, not neuron to neuron,
Mm.
but
So
manifold to manifold, latent variable to latent
I see.
variable.
Yeah, but this
Which
is again
is not
yeah.
a mechanistic model like you were
No, no.
asking. It doesn't go back to individual neurons, individual circuits. It's still using these constructed collective patterns of activity. But I believe that they are the building blocks, really, because
Yeah.
a network is wired so as it's very hard to take a network of neurons, not a neural network. You excite one of them, you put an electrode and excite one of these neurons. It's not the only neuron that's going to be active.
No,
It's going to
that's true.
generate a pattern of activity because of the connectivity. So patterns of activity, I believe, are the language that is being used to generate behavior and to communicate across areas in the brain or
Right.
to represent external stimulus.
So, but yeah, cool. But this is again electrical recordings. I was thinking like optical recordings with calcium imaging.
Aha.
Yeah. So that's because then you have a
That's a
slower
different,
time. Yeah.
that's an interesting question because that's certainly a different time resolution. Yeah.
Yeah.
Um, well, I have a collaboration with Hannah Will Schaffer, who works in the lab of John Disterhoff at Northwestern, and these are hippocampal recordings. And we have certainly found low-dimensional manifolds there,
Mm.
in not only on the place cells, which are typical behavior in hippocampus, but also in the response to an eye blink conditioning experiment.
Mm. Cool.
So the manifolds are there, and these are calcium
Imaging.
recordings. I am not so aware of calcium recordings in motor cortex, which is perhaps what you had in mind.
Yeah, no, I didn't really have anything in mind except optical recordings, and I don't really. I think of course, they have been used a lot in the visual system of mice,
Right,
so maybe
right.
not in. I'm not quite sure. Maybe it's difficult to get to it. I have no idea actually where the
Yeah,
motor
I don't
system
know.
for. No, I
Yeah.
don't know. So, but so I mean, what are the consequences? I mean, for brain machine interfaces, right? Then you put down electrodes and from an yeah, into the motor cortex, and then you want to have ideally to have some kind of signal that you can use to decode to maybe to have like paraplegic or quadriplegic steer robot arms or curse and so on. So what is so is your manifolds the way to go, or low dimensional manifolds? Is that important here?
The consequences are that we are very lucky that
Yeah.
this is the way the neural activity is organized,
Uh,
because it means that with very few degrees of freedom, we can control the external device. And the
mm,
external device could be a prosthetic arm, could be a wheelchair, could be something that allows you to translate. If you are an ALS patient who has lost control of muscles around the mouth, then you're isolated, but you're not affected at the cognitive level. You can dictate, you can imagine letter after letter after letter, and if I can record that neural activity and decode it into letters, you can.
yeah,
And there are people who write long messages this
yeah,
way,
yeah,
and the decoders have achieved speeds that are not comparable to a professional typist, but perhaps very
yeah.
comparable to me typing, which is a very
Mm,
non-professional speed.
mm.
So, and
That's
why are
right.
we lucky that way? Because the decoders that we create don't translate. Let's say I record 1,000 neurons. Don't go from 1,000 neurons to a few degrees of freedom. They go from 20 or 30 latent variables to a few degrees of freedom. So for us, it's much easier
Yeah,
to create these decoders, and it's much easier to generalize these decoders across individuals. So I would like to tell you about a monkey to monkey transfer,
okay.
and then a monkey to human transfer that was very
Okay.
exciting. So
Excellent.
the
Yeah.
monkey to monkey transfer goes like this. It's again the center out task. This is why I took time at the beginning to tell you about the center out task, because it keeps on coming back. So we have a monkey, as I told you, that has been doing this task for a long, long time. And we have a lot of data on this monkey. And we have created very good decoders that transform neural activity into kinematics, but also neural activity into muscles.
Mm,
Now, when I say neural activity, the inputs are not neuron 1, neuron 2, neuron 3, neuron 4, but latent variable 1, latent variable 2, So it's the degree of activation of the neural modes. Because we established a long time ago that we get equally good decoding with 10 neural modes than with 200 neurons. So these 10 neural modes capture all the information that is needed to be able to predict muscle activation, for instance.
mm,
So so let's concentrate on the muscles. We have the neural activity to muscle decoder in the what I will call the source monkey, the monkey for which we have enormous amount of data. Now we have a new monkey for which we have little amount of data. He's learned to do the task, but you don't have so much data. We can paralyze the arm of this monkey, and we can do the following. we are the monkey is looking at the task, so he's trying to move the arm but he cannot, but he's producing the neural activity that corresponds. So we analyze his neural activity, we find his latent variables,
mm,
and we have methods to align latent spaces.
mm,
So we align his latent space to the latent space of the source monkey. We use the source monkey to predict muscle activation.
uh,
We go back to the target monkey and we use electrodes, needles, to
okay.
activate the muscles according to that pattern,
Oh,
and the arm moves in the correct direction.
wow. Wow. Fantastic.
And we have, so that means that for this very simple task, the neural representation of different monkeys is similar enough. The
Hmm.
late so that we can align one latent space to another latent space.
Yeah. Hmm.
And then very recently, and we just published that, we have been able to do the same thing using our source monkey, and using a patient who is paraplegic. He has suffered a spinal cord injury
Hmm.
and he's paralyzed from the neck down. So he's watching a video of the source monkey and he's imagining doing the same movement with his arm to the
Okay.
top target, to the target to the right, to the target in between. He's imagining. We measure his neural activity. We have an electrode implanted. This neural activity is aligned with the neural activity of the target, the source monkey. The source monkey decoder is used to predict muscle activation, and we activate his muscles, and the arm moves in the correct direction.
Wow. So these are really
So we are
robust.
incredibly lucky we can do this because the latent variables, and this also shows that our latent variables are not just a convenient construct because it's easier to visualize a low dimensional space. So it's convenient for us to do dimensionality reduction and to describe the collective activity as compositions of a few latent variables. They have real meaning, they carry information. They carry task information.
Hmm.
Now, this also shows if I use 10 latent variables in a it's a 10-dimensional manifold in a very high dimensional neural space. This also shows you that there are many other things that neurons in motor cortex can be doing. One of them is having manifolds for other tasks.
Yeah. Yes, another way we've been lucky is that if you put down sort of this recording electrodes, it doesn't you don't all you need is to get like a sufficient amount of representatives from each manifold. You don't need any particular set because that would be
Exactly,
very 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 difficult. You just need
exactly. That would be very difficult.
yeah.
You know, these electrodes, we don't have control, we implant them. And it's the same thing with the neuropixels and with the multi-electrode arrays. You put them in and they record whatever they record. You don't
Yeah.
have control. You cannot
No.
say, I'm recording only pyramidal neurons in layer three.
No.
That's not an option. You know,
Yeah.
they record whatever
Yeah.
they come close to. Yeah.
So that's really yeah. So yeah, that's the creator has been nice with us in that respect.
Yeah,
I
yeah, yeah,
guess.
yeah.
Yeah.
We, but I don't know. Let me tell you two reasons why I think it makes sense that the brain is organized that way. One is at the input level, and the other one is at the output level. At the output level, all behavior has to do to controlling our muscles. So it's controlling a plant that has as many degrees of freedom as we have muscles,
Mm,
which is of the order of hundreds.
mm,
And if you think of muscles composed of sheets with fibers, maybe it's of the order of 1,000. It's not a million and it's not 10 million.
mm,
So if you need to control a plant that has 1,000 independent degrees of freedom, you only need 1,000 control signals.
mm.
So
Ah,
you don't need so it makes sense to construct low dimensional representations.
yeah.
because you're controlling a low dimensional plant.
Yeah.
Now you can say, okay, what happens in V1? What happens in primary visual cortex? So there is a very interesting paper. I don't remember the authors, but it appeared in a conference called ICLEAR, International Conference for Learning Representations, which is one of the big machine learning conferences. What they did is they took a very large database called ImageNet. ImageNet is a database that is used to train the deep networks for visual activities, for pattern recognition, visual recognition. Each image in ImageNet is 250 by 250 by 3. So it's of the order of 150,000 numbers. So every image is a point in this 150,000 dimensional space. ImageNet has 20 million images. So now you have 20 million points in 150,000 dimensional space. So they use the same methods for nonlinear dimensionality estimation that we use for the neural data. One method in particular, which is called Tullian's neighbors, it's a method by Levina and Bickel. They use it to estimate the dimensionality of this manifold. And now I will let you guess. Is 20 million points, each of them is a point in 150,000
Yeah.
dimensional space. Now, these are real images. These are
Uh,
images of things in the world,
uh,
animals, objects. They are not.
uh,
So, what do you think is the dimensionality that they found?
I don't know. Well, since you're asking, it's probably much lower than you would expect.
It's much lower than you would think.
So maybe I should give you a few hundred. I'm just very. This is just out
45, 45.
45 exactly. Yeah.
So
Wow.
this method has a parameter, and as you increase the parameter, the dimensionality estimate increases, and then it saturates.
I see.
So the parameter doesn't matter anymore. And that
Hmm,
dimensionality at which it saturates is 45.
hmm, hmm,
So the images that we respond to, our visual system has evolved to process images in the world, and these images are low dimensional.
hmm. Yeah.
Why are they low dimensional? Because there is a lot of correlation, there is a
Hmm,
lot of structure.
hmm. Yeah.
Like if somebody makes a caricature of you, I
Hmm,
would be able to recognize it.
yeah.
And I don't need the information about how the illumination is changing
Hmm,
slowly along your cheek.
yeah.
That's not relevant to
Hmm,
doing object recognition,
hmm.
right?
Yeah.
There is a lot of information that is redundant, there is a lot of covariance, and there is only a few features that are important. And those few features
Hmm,
determine low dimensional manifolds.
hmm. Yeah.
So that our representation of objects doesn't need to be as big as the dimensionality of the pixels in our retina.
Hmm, hmm. Yeah. Hmm,
Because again, they are latent variables. They
hmm,
are extremely correlated
hmm,
images.
hmm,
To me, that was a great discovery that they did that,
hmm,
because to me it's an explanation of why we have evolved brains that use low dimensional representations.
hmm,
Because at the input level, our inputs are generated by a world with correlations.
hmm. Yeah.
We are not exposed to black and white, so salt and pepper,
No,
or
no,
color.
that's true. Like the noisy when we did get back in the days when we were watching black and white TV with no
Exactly,
signals. This sort of like white noise kind of things. That's not what we're watching.
exactly,
Mm,
exactly. That's
so
not
that's
what
true.
we evolved to watch.
No, so
That's not what
that's
we evolved to watch.
no,
So we evolved to watch very structured, very correlated, low dimension images that live in the low dimensional manifold in the space of all possible arrangements of pixels,
mm,
right?
yeah,
So it's not surprising that our visual system develops
mm,
low dimensional manifolds for the representation of objects.
mm,
And all our behavior has to do with moving, with controlling a plant of muscles, which is again a low dimensional plant.
mm,
So why would we develop
mm.
very high dimensional representations of tasks.
Hmm. Yeah. Should
So
be
I think
interesting to see if there's some kind of, I guess different animals have different numbers of muscle fiber or separate muscle fibers, whatever. So it could be that there's a,
that would be an interesting thing to check whether the
yeah,
dimensionality of the manifolds is
affects
related to
the,
the dimensional. So you would expect animals with fewer muscles to have
yeah.
lower,
Yeah, I
lower.
guess like fish, for example, they must have
Yeah.
fewer. They don't. I would think.
So
Or
people have done a study of C. elegans
okay.
because, of course, there you know all the
Yeah.
neurons, and they have found a manifold which is very interesting. Goes, let me see if I. It goes like this. It's like a tube. It goes
Mm.
like this, and then it bifurcates into two, and then it joins again.
Oh. Huh.
And then what they can do is along that manifold, they can say here it's moving forward, here is moving backwards,
Mm.
here is turning right, here is turning
I
left.
see.
So
Okay.
different regions in that manifold correspond to different
Different sort of movements.
movements that this worm can make. Yeah. Yeah.
Okay, we're getting closer to the end there, but you're also, I saw that you're also involved in like interest in neuro AI. I guess you're also on a paper there, I think, on neuro AI. And so how can, well, what is your general thought of neuro AI? Or what is neuro AI to you?
Um, my work is no longer purely in AI. It hasn't been. First of all, I never work in AI. I
Mm.
work on machine learning,
Yeah,
and I think calling it AI is a little bit of a,
yeah.
a
Overselling.
overselling. Yeah.
Yeah.
Uh, but I no longer work in pure machine learning. I use lots of methods from machine learning to
Yeah.
create what I call this, to do what I call model-based data
Mm.
analysis.
Yeah.
So the methods that people develop in machine learning, like adversarial learning, transformers, all these powerful developments in
Mm.
machine learning give us, people who try to analyze real neural data, give us fantastic tools. So there is a lot of cross fertilization this way. The other way, there is some kind of cross fertilization in the other direction, probably less intense. So, for instance, the whole idea of the McCulloch-Pitts neurons
Mm.
and the perceptron, all these ideas came from neuroscience originally. So,
Mm.
when people construct neural networks nowadays, not necessarily transformers, but
Mm.
neural networks, even in deep learning, the neurons, the building blocks of these deep networks, are the old-fashioned McCulloch-Pitts.
Mm.
But that providing of a good idea was many years ago. Nowadays, I think that these manifold ideas, these
Mm.
ideas of looking for collective behavior, is something that, again, where neuroscience can
Mm.
perhaps lead the machine learning people who are very concerned about interpretability.
Mm.
Because they construct these networks, they work wonderfully, but it's very frustrating that we don't know why they work so wonderfully.
Mm.
And they work so wonderfully for this problem. Would they work equally well for other problems in the same class? What is the class of problems for
Mm.
which they would work well? And
Yeah.
what is the problems for which they would not work? And so
Mm.
there is a lot of things that we don't understand because we don't really understand why they work so well.
Yeah.
And so interpretability has become a big issue. And I think it hasn't happened yet, but I think that these ideas of low dimensional manifolds
Mm.
might help them
Ah. Yeah.
gain interpret, because that's the way I think now about the brain. I think we go for low dimensional sensory inputs to low dimensional neural representations to low dimensional behaviors, because our behaviors can also be understood as combinations of a few primitives.
Yeah.
And people have begun to do that in studying how a fly flies, or
Yeah.
how this worm moves.
That's sort of
You begin to see this synergy of behaviors.
yeah.
So I think that maps from manifolds to manifolds
Interesting.
are going to be more accessible and more useful than mapping all the objects, into all
Ah,
the neurons, into all the behaviors.
of course now. After talking to you, I started wondering why do we need so we have I guess 100 billion neurons on the order of 100 billion neurons. Why do we need so many neurons when we are so low dimensional?
To embed, to be able to learn many tasks.
Yeah, but we don't have whatever 100 billion tasks. I mean, it's
No, no, no. It's not a task, but it's
oh,
not
I
a
understand. I
neuron.
understand that, but I mean, it's not. It seemed like you talk about so like if you're like a thousand dimensional or a rather simple plant, then with only like
Yeah.
that. Why
No,
do we?
it's a good question. It gives us robustness. It gives
Uh,
us, um, and
hmm,
the other responses, and maybe that each area of the brain is doing many more things that we are
yeah,
not even aware
exactly,
of because we're not
exactly.
looking at it.
Yeah, that's
For
true.
instance, my colleague Juan Gallego has made a beautiful plot. Let me try to explain it. So, the y-axis is performance, and the x-axis is number of modes, number of latent variants, number of principal components, let's say. So, if you look at the variance accounted for, it raises very slowly.
Hmm,
But now he asks about muscle prediction.
okay,
And so he puts here little circles that said, this is the performance of muscle prediction that I attain using all the neurons.
okay.
Now he starts doing one principal component,
Uh,
one and two, one and two and three, one and two and three and four. So he keeps increasing the dimensionality of the latent space. By the time he gets to 10, he's doing as well as if he had used all 100 neurons. However, the variance accounted for, if I want to reach 90%, I need 40 or 50
okay.
latent variables, which means that there is a lot of stuff going on in M1 that is not controlling the activity of those muscles that I'm monitoring.
Yeah.
So perhaps we see very few tasks or very few because we are not monitoring all the things that M1 is doing. People who have studied, what is the name of my colleague at okay, then it will come to me in a minute. This is at Einstein School of Medicine in New York. They have studied V1 to V2 communications. Byron Yu is one of the authors in the paper. And they talk about communication subspaces. Because if they look at variance accounted for in V1, they find one subspace. But if they look at the neurons in V2 and they ask which directions in V1 are affecting me, they find a completely different subspace.
Huh.
So the subspace that V1 uses to communicate with V2 is not the subspace where most of the V1 activity is.
I see.
Which means there is a lot of, although we think of V1 talks to V2, who talks to
Huh.
V4, we think that this layer, there is a lot of stuff going on in V1. Part of it is giving feedback back to LGN, right? Which is not communicated to V2.
Yeah.
So perhaps we have this question that you ask, why do we need so many neurons if we are using so few? It's not that we are using so few, it's we are limited in our imagination of what these neurons are being used for.
Yeah.
We are not asking all the questions that can be asked about what
Yeah.
the activity, the neural activity is being
I
used
guess
for.
our imagination has historically been sort of hampered by the fact that it's very difficult to have very complicated tasks in the lab setting, right? So we're used to thinking
Right,
about not too complicated tasks, but of course,
right, right.
well, I think this is really important. This whole development of these manifolds has been extremely important for neuroscience, and of course, it has sort of both the theoretical development has sort of been well followed by the technology, or at least being in parallel with technology, and also computers, which allows for this analysis to be done fairly comfortably, right? So you don't,
Absolutely,
yeah, so that you
absolutely.
can do
Yeah,
this
yeah.
on,
Is the technology recording the conceptual the ideas and that came from techniques that have been available to us forever.
yeah, yeah,
Principal component analysis and
well,
things like that, which is when we first found this, and then more recent developments in differential geometry that allow us to describe nonlinear manifolds. And then, as you point out, the
so
ability to do complex analysis and large scale analysis because we have the computer power to do it.
So did you learn general relativity in Buenos Aires, or I
You
guess not.
know,
It would have been useful.
the truth is I did not.
No, me
I
neither. I never learned that.
I learned spatial relativity, but
Yeah.
I had a wonderful teacher when I was an undergraduate in my advanced electricity and magnetism course, who taught us the G mu nu and the
Ah,
T mu nu.
yeah, yeah.
So I learned these formulations about
Okay.
tensors
Yeah.
and covariant and contravariant
It's
and
interesting how
all this
these.
kind of differential geometry that is very useful when you talk about nonlinear manifolds. Yeah.
Yeah. So I guess like this Riemann who helped the mathematician, and well, Riemann and others who helped Einstein to, well, gave Einstein the formalism he needed. The same kind
Exactly.
of formalism is also very useful for us.
Exactly,
Yeah.
exactly,
Yeah.
and I think you haven't asked me about this, but I will say it because
Yeah.
I think that a physics education is a fantastic background education
Yeah.
because it's an education, it's not a profession. It's
No,
really an education.
that's
It
true.
really gives you a conceptual framework and the mathematical frameworks and the computational frameworks to study, to look at any problem in
Uh,
nature that you might want to look at,
yeah.
really.
Cool.
I think it's
So yeah. So now, now we are sort of approaching the end here. So maybe some like advice to the next Sara Solla or whatever, the young
the young
researchers, young students. Yeah.
the, okay, so when you're a student, both an undergraduate and a graduate student, you should think of this as an amazing opportunity that you more or less can survive, hopefully without having to work outside many
Uh,
hours. And your job is to study. And
uh,
this is an amazing time in your life. And you should take advantage of this opportunity to learn as much as you can. I think that how good a scientist you will be later on depends on your toolbox. And your toolbox is mostly acquired during those years when you are an undergraduate and a graduate student and a postdoc. This is when because if a colleague comes to me and says, what do you think about this? And goes to the board and starts outlining a problem. If I can map it into something that I've done before or seen before, I know how to start. It gives me like you pull from the beginning of the string and then you can keep on pulling and maybe later on you'll develop something new. But at the beginning, if you can attack it with something that you already know, you can get started. You can, take the first few steps. And how likely that is to happen depends on the size of your toolbox. So the bigger your toolbox, the more likely that is to happen. So build a toolbox. This is my most
so what
important
what is the
advice.
toolbox then now? If you think
Learn
about.
contextual techniques, learn mathematical
Yeah.
techniques, learn numerical techniques, just gather make your when you finish your postdoc, your toolbox should be really very rich, very broad and very rich, because then you keep on adding, but it's at a completely different rate,
Yeah.
because you never have the time to only study.
So.
You have other obligations and you have to teach and you have administrative obligations and you try to do your research.
Yeah.
But even now I have a pile of 10, 20 papers that I have scanned skid, but I want to study them, and I
Yeah.
haven't had the time to sit down and really study them and understand what they did and how they did it and why they did it. And so this is my main advice. And then later on, just science is not done a crazy scientist alone in a tower where
Yeah.
it's not done like that. It's collaborative. Develop good collaborations,
Yeah.
explain your point of view, listen to other people's point of view, cultivate your good colleagues, and then have a
And I
good time.
guess one new thing now is that it's. I mean, obviously I mean, you told about like your environment at Bell Labs and these places. And of course, when there was like personal meeting, which is the best, but nevertheless, it's also possible to at least sort of keep up collaborations over internet, and that's at least my experience. So
Yeah,
because one thing that is, that's actually one of the reasons I started this podcast, is because to try to make a truly global community. Because I mean, obviously there are many Argentinian scientists I met in, well, Europe or North America, but it's not too many people from Latin America that work in Latin America and come to meetings in Europe,
Right,
and because obviously for practical reasons it's probably
right.
expensive, all the meetings and so on. So trying to take advantage of this wonderful thing, internet, which has, well, many things from internet, which is not so wonderful, but at least from a collaboration point of view, there's many opportunities.
Yeah, I I think that sometimes at the beginning it's important to try to have some personal contact, but
Absolutely.
once you have established that, it's very easy to maintain a long collaboration only on Zoom.
Mm. Yeah.
And actually, sometimes I have had collaborations with people that I never met in person,
Yeah.
actually.
Yeah.
Collaborations that maybe started at the time of the pandemics. And
Mm.
again, in a forum where there were different people from different institutions attending. And then
Yeah.
we said,
Mm.
oh, you made this comment. I would like to pursue what you meant. And then we
Mm.
start talking. And then some idea comes out and it
Yeah.
becomes a joint collaboration. And I have two people that I have collaborated with that I enjoy very much working
Mm.
with that I've never met in person.
Yeah. Yeah.
So it's totally possible,
And
and it plays a very important role. Particularly, one is the role of accessibility that you just described, whether people can go to meetings, go to other
mm.
institutions, and the other one is has to do with how interdisciplinary this field is.
Mm. Yeah. Yeah.
You know that you don't always have access to those components in your own institution,
Mm.
so you
Yeah.
have to look for them
That's also
somewhere.
true. And now, also, which is very important, is that earlier you need to maybe to be at a big place doing experiments in order to get access to experimental data. That is no
Right?
longer the case, right? So, and you can also get access to supercomputers, and
Yeah.
like in the eBrains project where I'm involved. So if you have a good internet connection, you sort of, in some sense, you have access to a lot of the things. Of course, it's always better maybe to during in well when you're a student and a young researcher actually to have to physically collaborate with experienced researchers and be in
And
a
now there is more and more emphasis on putting databases, make them accessible. You know, the Annan Institute has been great that way
absolutely.
in making these databases accessible to people. So you can have an idea and you say, but I would like to try it in a good database to see if it works. Does it scale up? And
Yeah,
now they are available.
yeah,
And if you also can have remote access to good computing resources, then you can do it even if they are not
mm,
immediately, you know, they are not next door or in the next in
mm,
the other department in your same institution.
cool.
Yeah.
Okay, anything you want to say before we close for tonight or
No,
tonight
no,
here in Norway?
thanks a lot for the invitation, and thanks a lot for doing this. It has, as you
Yeah,
pointed out, this very important role
yeah,
of making people,
yeah.
creating a community and making people that are
That's
not
true.
necessarily talking to each other more
That's
aware of
true.
each other's work and more
Yeah,
aware of the ideas,
yeah.
the powerful ideas that are circulating
That's
around.
true,
So
especially for people who is, I mean, if you're a really big university maybe or big research institution, people come by and give talks. But that's, I think, often people doing theoretical neuroscience are, they're often quite alone at the university because it's a minority activity. So
well, sometimes when you're in a neuroscience department,
yeah,
you don't have the quantitative bodies. You
mm,
know, when you have a theoretical problem,
yeah, that's
you
true.
know, an equation that you don't know how to
Uh,
solve or how to solve a numerical convergence
yeah,
problem, you need a community of your peers. And your
mm,
peers are not necessarily the neuroscience
that's
department.
true. No,
Sometimes
that's
you're
true.
the only theorist in the
But
neuroscience
of
department.
course, I'm happy that you say nice words about the podcast. But of course, I can let you in on the secret. I mean, the privilege of me, for example, picking your brains now, which is the world expert on this, for 2 hours while sitting in my office in Norway. I mean, I couldn't do that without the podcast, right?
Exactly.
so so nobody. So
So
making a podcast is a very nice opportunity and a very nice thing for keeping me well.
it benefits everybody, and of course people can access your earlier podcasts
Absolutely,
also.
I have a nice
So
collection of
it's all in a repository, and
absolutely.
everybody can access them.
Absolutely.
That's a fantastic tool for the community.
It is. Excellent. Well, thanks a lot, Sarah. It was really, really nice to talk to you.
Thank you, and thanks a lot for the invitation and for the work that you do.